Hey guys, welcome back. We're going to be talking about inferences for regression. This is our last topic that we have pretty much for all of the AP Stat material, so pretty exciting. So this is inferences for regression. So we talked about in Unit 2 with bivariate data, which is one of my favorite units, by the way, creating lines of best fit to be able to basically doing regression, minimizing our least squares, residuals, all that good stuff, to be able to come up with a model that best summarizes data between a relationship between two variables. As our explanatory variable grows, what happens to the response variable, in other words. Now we realize that no model will fit it's useful, especially if we can straighten it out, but no model is going to fit the data exactly. There's going to be residuals or error from those residuals, which is another way we call it, and specifically a standard deviation of those residuals where our model was off by a certain amount, like an average standard deviation for those residuals, for how close or how off our model is. We're going to be able to look at that in more depth to be able to come up with prediction intervals for how well, basically confidence intervals for that regression model, and also confidence intervals for what we think the true slope might be. Instead of just summarizing it with one model, that we could actually find a whole family of models that what we think the slope might actually be. So that's what we're going to be getting into. It's actually kind of cool, pretty intuitive. It kind of just naturally follows what we've been doing with inference, if you just have to remember what we did with bivariate data as well. So predicting body fat is kind of an expensive process. They actually, if you read like the first chapter in the book, you can read more about it if you're interested, but they actually take 2 x-rays, I believe, and between the two it takes about a 10 to 15 minute process, so of course that's going to be pretty expensive. Then they're able to accurately predict your BMI, or sorry, not your BMI, but your percent body fat. So since that's kind of expensive, it takes a lot of time as well. They want to know if there's any other measures that they could use to be able to accurately predict body fat, such as using waist size. So if you tell me your waist size, how close do I think I can get to predicting what your actual body fat percentage would be? So let's talk about percent body fat, because it is actually different between men and women. So the essential percent body fat that you absolutely have to have for men is 3%. So you can't have anything less than 3% body fat, but for women it's 12.5%, which is quite a significant difference. Now with the healthy range for body fat for men, I think it's between 18 and 20 or 39, and for women 18 to 39. For men it's 8 to 19%, but for women it's 21 to 32%, which is entirely above the range for men, so completely different. So whenever we are finding whenever you are interpreting percent body fat, just keep in mind it is different. We should interpret those values differently between men and women. All right, so here's a scatter plot that we have for all the waist sizes of 250 men. They gathered the sample, I think, back in 1990. They went through the expensive process of accurately measuring their percent body fat, and then across their waist size. So we're trying to see how well is your waist size a predictor of your percent body fat. So this is our explanatory variable, this is our response variable. So this gives us our model, the percent body fat predicted, which is why it has the hat over the top, is equal to our y-intercept plus our slope of 1.7 times the waist, which is our explanatory variable. How does the waist size explain our response variable, which is what we're interested in, the percent body fat? So this was a sample of 250 men. As I said, we have our scatter plot here. It looks linear, so one of the things we're always looking for to see if we need to re-express the data, but it does actually look linear. And it looks like it's an even spread all the way across there as well. So the question we might have is how close was our slope, which we calculated from our regression of 1.7? How close is that to the true slope? Now remember, this is just a sample of 250 men. If we did a population of all men with all their waist sizes down from like 28, the smallest waist size that we would have, to the largest possible waist size, which I don't know, 48, 50, something like that, there's going to be a true slope, right, of that regression line. But we did a regression line for our sample. So as we change a different sample, we do another sample 250, our slope's going to be different for that one as well, depending on the sample. And so there's going to be variation. So the question we have is how close is our slope of 1.7 to the true slope, which will be using beta. So we're using the Greek letter for the parameter for the actual population. The Latin letters would be for the samples, of course. So we're going to test a hypothesis, which is pretty common to test the hypothesis. What is the probability that the true slope is actually 0, which would mean that there was no association between waist and percent body fat, meaning as you changed in your waist, you were not allowed to change at all in your prediction for the percent body fat. So we would just simply give out an estimate of the average percent body fat for regardless of what your waist was. So that would be what we would mean by a true slope of 0. So we want to find the probability of this occurring. What's the probability that there really is no association between the two, meaning that we are not able to remove any of the residuals or any of the error in the percent body fat by using the explanatory variable of waist. So then the next question we might ask is, what is the margin of error with the 95% confidence interval? Which essentially, once we have our model, what's the margin of error at any point within 95% confidence that we are capturing the true mean for that waist size? So no matter where we're at, like if we get put in 40 here, so we do 1.7 times 40, then we subtract negative 42.7 from it or whatever, that's going to give us a single value out. But the true value is going to be between those somewhere, will be somewhere around that value within a certain margin of error with 95% confidence. So that'll be the next thing for our predictive values to be able to capture that. So whenever let's say that we plot these values, we look at all the people that had actually 30 inch waist, and then we have the mean for that, okay? And then over here we have 34 inch waist and the mean for that. And so these red dots here are the means. Now, ideally, these means would all be on our line of best fit, but of course that's not actually going to happen. We're just reducing the least squared residuals, so this outlier, this value here, would have a pretty big impact on it, which could actually change it and kind of knock the whole thing off. So we got to be careful with that. So on top of that, we can look at the total percent body fat to make sure that our population looks like it's normally distributed. It does look like it's normally distributed, which is good. And then ideally, on top of all of these, if we broke them all down, we would have a bunch of samples of all the people that had size 30 waist, all the men that had size 34 waist, and then whatever these are as well. Now, each one of these needs to be normally distributed as well, or at least the sample needs to suggest that the population was normally distributed. And if it did look like we had any outliers or any skew data, then it might throw off some things, especially the outliers. So we might have to remove certain outliers so that they're not increasing the standard deviation of the residuals and throwing off potentially our how well we can predict the actual true slope. So we do need to look at these values as we go across here to make sure that the spread is even as we go across and that we don't have any outliers. So the true regression line from population, let's say that the true regression line is actually this red line here, but from our sample, we actually got a regression line, which is the black line. Now we know those are not always going to be exactly the same, and so that's why there's going to be a standard deviation or standard error for the actual slope that we're trying to estimate. So whatever the true mean is for that value at y, that's going to be equal to the true y-intercept plus the true slope times x. Now the problem is that there's always going to be residuals, and so we can actually plot the actual values by adding this error to it, which is going to be the residual, whether it was how far above or below our prediction was from the actual true value that it should have been. So if we look at the residuals, that also should be a normal plot. We need to make sure there aren't any outliers in that. That could also help us figure out if there's any points that we need to remove. So there is going to be a disconnect between the actual data and the model and from our sample and the population. So quite a lot going on here. Hopefully you can follow. So another thing that we have is as the sample size grows, the central limit theorem will actually kick in. So these are just snapshots of small samples of all the men that have size 30 waist. As we increase our sample size, what's nice is that it's actually going to turn into a bunch of bell curves. And so ideally speaking, they would all be centered. The means for 30, 34, 38, whatever, would all be centered along that line, which we know they're not going to be. And they would all eventually, with a large enough sample, turn into bell curves as well, using our central limit theorem. So that's the idealized regression model, but of course that's not exactly what's going on. We just have to make sure that it's not too far off so that it would throw off our regression analysis. So assumptions and conditions. First one is a linearity assumption. So we need to, just like before, we need to make sure that we believe that the scatter plot is straight and that it can't be straightened out. So if there's any curvature, a good thing to do is always to graph a line, the straight line like a line of best fit, and then check it against that line to make sure that you don't see any subtle curvature. Another good way of doing it is actually to graph the plot of the residuals at the end and then make sure that there's no curvature or pattern in the residuals. So this is the straight enough condition. So we're assuming that that's actually linear, that the population is linear because it looks like the sample is straight enough. We also need to make sure that we're dealing with quantitative data. If we graph categorical data, it's going to look pretty choppy across the board. And also categorical data does not have any natural flow of what should be in front. So like if we were doing colors, like eye color, where does blue go in comparison to green, in comparison to brown or the hazel? It doesn't make any sense. So make sure you're dealing with quantitative data, and it's appropriate to be doing bivariate data and looking at how the two variables relate to each other as well. So the second assumption that we have is independence assumption. So is it really a random, independent, or representative sample? So if we see any pattern in the residuals, that could show us that there's something else going on. As we plot it across time or something like that, that may be that there was something going on and it's not actually truly independent. So when we're looking at the residuals, we're checking for patterns, usually curvature that needs to be straightened out. Are there any trends, anything that we're noticing there, any clumping? In other words, are there is the variation going to be even across the board, or do we have something called fan behavior? So here we have equal variance assumption, which is also really important. So does the plot thicken? So in this case, the example they gave in the book was the cost of, or the value of a diamond, but depending on the weight of the diamond. So smaller diamonds all have very consistent values, but as we get larger and larger weights of diamonds and carats or whatever, their values become more spread out. So there's much more variation. So we can't this is not actually appropriate to use, because as we get higher and higher, our standard deviation is going to increase, and our model's pretty much going to fall apart. So it's better at certain times, but especially at the very beginning with smaller sized diamonds. But as we get larger, it gets really big. So that would be what we call fan behavior. We have to be careful and be aware of that. So we need to assume that the variation is even all the way across. So all the way across the line, that they're all even. That way we have the same predictive strength at the end of the model as we do at the beginning, or even towards the middle of the model. So also we have to assume that the normal population, that the population is actually normally distributed. Otherwise it wouldn't be appropriate for us to be using all of our t-distributions and our Gaussets models and stuff like that, which the whole thing is based on essentially. So we need to make sure that whenever we graph the residuals, that they show that they are normally distributed, which is what we're showing here. Essentially, like if I plot this across the line and I capture all these points, that's what this plot of the residuals of the histogram is really giving us. So kind of a visual of what's going on there. Another way that we could check to see that it's normally distributed is to graph a normal probability plot, which you can do that from the calculator. That graphs the normal scores across the residuals, and it should be linear. We can actually graph a line to check to make sure it is linear. So here's the computer output that we got for all this data. Now, typically we're dealing with large data sets, like over 100. In this case, it was 250. So it's not something that you're going to be putting into your calculator. Most of the time, this stuff you're going to be using Excel for, and it'll actually, or some other statistical software, will actually give you the output of the regression. So here's the computer output for this regression. So our dependent variable is the percent of body fat, which is going to be our, in other words, our response variable. That's the dependent. The independent variable is going to be our explanatory, which would be waist size. The R squared, which is also called the coefficient of determination, it's just your correlation coefficient squared. So we can actually find the correlation coefficient by taking the square root of the R squared, which would give us 0.823, just in case you forgot that from unit 2. So the R squared is coefficient of determination, tells us that 68.7 or 6, sorry, wow, dyslexia is worse. 67.8% of the variation and the response variable can be accounted for by the variation and the explanatory variable by the model. Okay, the next thing that we have is denoted as S. Sometimes it's actually denoted, it's the standard deviation of the errors. So sometimes it's denoted as S sub E, which is the residuals, basically standard deviation of the residuals, which is the overall standard deviation of how far off the actual data points were from the model itself. So basically kind of giving us a predictive strength of our model in real world units, which is kind of cool. With 250 minus 2, which would be 248 degrees of freedom. So the reason we're subtracting 2 is because we're estimating 2 parameters instead of 1 this time. We're estimating the slope and the y-intercept. So then we have our 2 variables, which we have the intercept, which obviously would be the y-intercept. We're pretty much not interested in that. It's not really that interesting. It does give us the coefficient for that, which is this negative 442.73, which is our R-intercept, okay? So that's what that is. The standard error of that, the t-score, which is the basically how far it is away, 0 would be away from that, and the probability of it actually being 0, we really don't care about that at all. What we're interested in is the other one, which they're saying is waste. Now that's going to be our slope. Why they call it waste, I don't know. That's telling us that this is our dependent variable, so this is the independent, so that's the response, and this would be the explanatory variable, which is waste. So we're using waste to predict the percent body fat. So anyway, that's what they give you in the regression analysis. So anyway, the coefficient of that is 1.70, which is our slope. The standard error for the slope is going to be basically 0.0743. The t ratio, which is like a t-score essentially, is going to be 22.9, meaning we're 22.9 standard deviations or standard errors, pardon me, above the above 0. So the probability of that actually being 0, meaning there is no association between the two, is less than 0.001%, which is what we call statistical 0. Now, putting all that together, mainly the two coefficients, these are kind of important, and we'll really just be jumping to the p-values as well, mainly that p-value. But anyway, putting the coefficients together gives us our regression, the equation of the regression. So kind of cool. So what affects the standard error of this sampling distribution model with slopes? Which population distribution would yield more consistent slopes? So the spread about the line. So if we looked at the line, basically graphing out across here, which one's going to have the most spread about the about our regression equation? Well, if it's much more consistent like we see here, then we're going to have a much smaller standard deviation of the errors. There is still spread. There's always going to be spread. When we graph out the residuals, there's always going to show it as some spread, but we put that into context, that's much less spread than we have over on this one. Even though they would have the same slope, this one's going to have much more variation for the slopes, meaning we think it's much more likely that we could have the true population slope could be much more varied around this data, because there's much more standard deviation for the residuals. Now in this one's much more consistent, so we're pretty confident about the actual slope, and we'll have much more predictive 95% confidence intervals for the predictive values as well. Okay, then spread around the axis. So whatever the standard deviation of the x variable is, if it's very consistent, then that's actually going to make the slopes pretty unstable. Now, if we have a much larger standard deviation for the x, the explanatory variables, meaning you have a much wider range of values for like waist sizes in this case, then that's going to actually give us much more consistent results. So much more consistent values for the slope, because it's all spread out. So as we are going across this large standard deviation, we're able to track the changes in the y variables more, as it kind of makes sense. All right, also the sample size. So as you would probably expect, the larger the sample size, the more consistent we are, the more confident we are about actually capturing the true slope. With smaller samples, it's going to vary much more. So we have some outliers on the bottom. If we took another sample of, I don't know, 50 or whatever, we might have outliers on the top side, which would actually change the slope quite a bit up high. So larger sample size is going to increase our confidence that we have the true slope, or that we're closer to the true slope. So those three things put together give us the standard error for the slope, for the regression for the slope, the standard deviation of the errors. Of course, we want a smaller value for that one. And then on the bottom, of course, if we have a larger sample size, that's going to decrease the standard deviation for the error for the regression for the slope. Also, the standard deviation of the x, as we have a larger standard deviation of the x, there's more spread around the x. It allows us to kind of zoom in and be more accurate and precise about that value as well. So we want to increase these and decrease that one. So those are the three things that affect more consistent slopes. So given our sample where we had our one value for the 1.7, which is our basically the our best estimate based on our sample for what we think the true slope is, what is the probability or the p-value that the actual true slope from the population, not from our sample of 250, is actually 0. So to do that, we're using t distributions, which is kind of nice. So Gauss's models, and with n-2 degrees of freedom, because we are estimating two parameters for slope and y-intercept. So that would be 248, so 250 minus 2 essentially. So the t value for that, which is like a z-score, but it's a t-score, is whatever our slope was minus the hypothesized slope of 0. So basically we are 1.7 above that. So 1.7 divided by the standard deviation, or the standard error for the slope, which is the standard error for the coefficient, which is this value right here. So basically 1.7 divided by this is giving us a t-score of 22.9, which gives us a probability of a statistical 0 that's not going to happen. So our final conclusion is that we believe that our best estimate that the slope is a 1.7, and that the probability that there is really no association between the two, which would mean that the true slope is actually 0, is less than 0.001%. Meaning it's not going to happen. Again, that was with a t-score of 22.9, which is going to be way out there. And with a larger degree of freedom, like closer to 250, it's going to be really close to a normal model. So, I mean, it's going to be even more significant. That's why we have to use our p-value for that anyway. So there's actually two different margins of errors that we're dealing with here for 95% confidence. One is 95% confidence for the slope. So we're 95% confident, that's going to be the green values here, by the way, and the green values here. We're 95% confident that the true slope is somewhere between those values for the different values of the slope. Okay, so that's regression analysis for the slope. We do that quite often. The other one that's much more useful, I would probably say, is a 95% prediction interval. So we have our best estimate, which is our line of best fit, and then we want to be able to say, okay, so wherever we are, whatever waist size you're at, we want to be able to create a confidence interval at that waist size that we believe within 95% confident that, or 95% of all the data would actually fall between those values. So we think that your true percent body fat would actually lie between these two values if you had a size 40 waist, a man with a size 40 waist or something like that. So that's much more practical, but oftentimes if we're trying to see if they're for evidence of an association, we're doing inference, regression inference on the slope itself. Okay, so we're going to specifically just be talking about the slope. The prediction intervals can be done, but we'll deal with that later, okay? So how well can we predict electrical usage from outside temperature? So our null hypothesis is going to be that there's no association between those two variables. So outside weather does not impact the electrical cost. So in this case, our explanatory variable would be the outside temperature. Our response variable that we're measuring is the electrical cost. The alternative hypothesis would be that there is an association between the two, which would mean that there's a linear association, meaning that the true slope is actually not equal to 0. If there was no association, then the true slope would be equal to 0, meaning as we increase in temperature, that does not change the value that we were able to estimate our prediction for the cost. We would just have to estimate the mean cost, regardless of what the temperature is, meaning the true slope is actually 0. So let's check our assumptions and conditions. So here we have the plot. So it looks like as the temperature goes up, the electrical cost goes down. That's because we're looking at lower values. So obviously they're using heating. Of course, as the average temperature goes up beyond 70 degrees, people are going to be using more electricity because now they're cooling it. So we only look at colder temperatures in this case. Otherwise, it would not be linear. But apparently, around 70 degrees, people stop using a lot of electricity. So we have our line of best fit. Once we do our regression, we can plot the residuals. It'll give us the graph of the residuals. So it does look like we might have some curvature here, so it might not be appropriate. And then if we look at the residuals here, it does look like the plot of the residuals does not show. They look essentially like they're nearly normal, so it doesn't look like we have any outliers that we have to deal with. Even these high values here look like they're probably okay. They're within line here. Keep in mind this is a pretty small sample, so if we had more data, it would probably fill in nicely. I don't necessarily think there is a pattern here, but it's kind of hard to tell because it's such a small sample, really. All right, so straight enough condition, yes, it does look like this is linear by checking the plot and the residuals. Independence, random assumptions, so they should be independent of each other. It doesn't look like we have any patterns in the residuals, no fan behavior. It's not like it's changing, becoming less or more variation across any value of x. So that should be fine. Equal variance is a plot thickened, so no, it doesn't look like we have fan behavior here. It looks like it's pretty consistent across the board. You could say it was even more consistent here, and then it started to get where there was more variance across the middle and the around the 50s and 60 degree temperatures outside, but again, that could just be because we have such a small sample. Nearly normal outliers, doesn't really look like we have any outliers. There's not like a gap in the data here because there's just one bin that's missing. If there were multiple bins, then we could say there was a gap and those would be outliers. So I think we're good to go. Is there evidence of an association between the average monthly temperature and electrical usage? So looking at the output here, our coefficient for, and we don't really care for the constant, but for the average temperature, which would be our slope, is -50. With this standard error here. Now they're going to tell us that the T ratio or the T score is -10.2, which we know is anything higher than 2 is going to be pretty unusual, except with Gauss's distributions, of course, with really small sample sizes, we would have really wide tails. Don't forget about that. But anyway, they'll give you the actual p-value for that appropriate Gaussian model. So they're not going to give you the actual p-value at some point if it's lower than 0.0001. They're just going to say it's less than 0.001, which is what we call statistical zero. So statistically significant at any reasonable alpha level, we have enough evidence to say that there is an association between monthly temperature and the electrical usage. All right, explain the association using a 95% confidence interval. So that's where we're going to need this standard error of the coefficient. We also need to know how many standard errors we need to go out to capture 95% of the data. So we're going to use an inverse T distribution to capture basically 95% of data would have 2.5% on both tails. So you can either go all the way up to 0.975 or 0.025, measuring from the left or measuring from the right. It won't really matter. It'll just give you a positive or a negative t-score. So essentially that's going to give us 2.228, which is our critical value. That's how many standard deviations or how many standard errors we need to go out. So if I multiply the number of standard errors times the standard error for that coefficient, which is our slope, that'll tell me the margin of error. So I'm going to add and subtract the margin of error, which is this value, from our mean, which is our estimate for the slope, our best estimate for what we think the true slope is, and that'll give us an estimate for the slope. We're 95% confident that the true slope between average monthly temperature and electrical usage is anywhere between -61 point, basically -62, and -40. And then that would be in units of whatever our y is over our x. Okay, so because 0 is not contained within that confidence interval, of course, we think that there is a difference between the two, so there is evidence of an association, and we're 95% confident that the true slope of the regression of the actual populations between those two values. All right, well, that's it. Sorry I went a little bit long. This is quite a bit of stuff. If you want to read the textbook, I think we're doing about 10 pages. You can see it on top of the assignment. Probably a good idea to go through that to really let it soak in. And I'll see you guys later, so have a good one. Bye-bye.